Welcome everyone to our 56th iteration of SPCLBcast. Today we're having John Mellor-Crummey, and Martin will introduce John.
Thank you. John is a computer science professor at Rice University whose research focuses on performance measurement and analysis with contributions ranging from scalable synchronization algorithms to dynamic data arrays detection and network performance optimization. He co-led the development of the OMPT-Tools interface for OpenMP5 and has been honored with awards including the Dijkstra Prize, a US Secretary of Energy Honor Award, and the ACM Fellowship. So without further ado, the stage is all yours, John.
Thank you. Okay, can you see my slides?
Yes.
Okay, so today I'm going to tell you about the work that we've done on the HPCToolkit performance tools as part of the DOE Exascale computing project. So just first a bit of history. We got started on the HPCToolkit project to help ourselves optimize code for complex microprocessors. And so initially we had some funding from the Department of Energy to work on compiler support, and this was back in the late 90s. And we came to the realization that we had no idea why programs were slow. And so instead of building compilers, we started working on using compiler technology to build performance tools. And so that was the start of the HPCToolkit project. So in recent years, as part of the Exascale project, the focus has been on building performance tools for the DOE's Exascale supercomputers. And the three computers, I'm sure you're aware of what they are. They have different GPUs in them, two from AMD and one from Intel. And so that's complicated. That complicates the problem of building tools because we've got different GPU hardware and different measurement interfaces from each of the vendors. So some performance analysis concerns for GPU accelerated supercomputers. Well, one thing is you want to make sure that you have good computation performance. We need to keep the GPUs busy and productively engaged with extreme scale parallelism. We need to minimize data movement costs within and between memory spaces. We care about communication costs between the nodes and also I/O. And there's lots of ways where we can hurt performance with insufficient parallelism, load imbalance, serialization, replicated work, inefficient implementation, you name it. And the challenge is that the hardware and execution models are pretty complex on these systems. We have CPU and GPU compute engines that have vastly different characteristics. There's multiple memory spaces, memory space for the CPU, memory space for the GPU, and asynchronous execution that you can offload kernels that execute asynchronously on the GPU while the CPU is still running. So some measurement challenges for GPU accelerated supercomputers. Well, first we have extreme scale parallelism. And so any serialization within the tools will disrupt parallel performance. And so what that means is that building concurrent data structures inside the tools is something that's really important. There's also multiple measurement modalities and interfaces, and I'll say more about that in a minute. There's the potentially frequent GPU kernel launches that require low overhead measurement. And another thing that's important is that there are third-party measurement interfaces that we have to use. So the tools can only measure what the GPU hardware can monitor. And so we have hardware performance counters and then also some support for instruction level performance measurement that I'll say a little bit about in a few minutes. And then we use the Linux perf event interface for measuring on the CPU, including inside the kernel. And we use the GPU monitoring libraries from the vendors. And so from NVIDIA, that's the CUPTI performance monitoring library. From AMD, that's their Rock Profiler SDK. And then from Level 0, well, we don't have a library. We just get to use their Level 0 infrastructure. So in this talk, I'm first going to describe a bit about the HPCToolkit performance tools and give an overview of their components, and with not just talking about like what they are, but also digging in a little bit into their internals to give you a sense of what's going on. I won't have a chance to talk about it all completely in this talk, and so there's a lot of citations throughout that indicate where there's a more detailed description about those aspects of the tools, and I'll provide a copy of the slides afterwards so that they can be posted and you have all the references. And then after describing HPCToolkit, I'll show you a little bit about analyzing the performance of GPU accelerated codes with HPCToolkit with a few examples that illustrate some particular capabilities in HPCToolkit. I'll describe some ongoing concerns and some ongoing work in the project. So HPCToolkit was originally developed by Rice University, and last year we migrated the copyrights and whatnot from Rice University to the Linux Foundation as part of the High Performance Software Foundation. And so what you can do with HPCToolkit is you can collect profiles and traces of unmodified parallel CPU and GPU accelerated applications. And with these profiles and traces, you can understand where an application spends its time and why. And so call path profiles associate metrics with application source code contexts. And in particular, we analyze instruction level performance within GPU kernels and attribute it to your GPU source code. And then hierarchical traces help you understand the execution dynamics as a program executes. So we support a wide variety of programming models, and so typically using MPI across nodes, but you can also use things like SHMEM and UPC++. Within nodes, there's a large variety, and so CUDA, DPC++, HIP, Raja, Cocos, OpenMP, and the language is pretty much any compiled language, and we also have support for Python in addition. And so for hardware, x86 power and ARM CPUs, why does it matter what CPUs we're using? Well, we're doing binary analysis of the CPU code. And then the GPUs, NVIDIA GPUs, AMD GPUs, and Intel GPUs, we're also doing binary analysis of the GPU code as well. So why use HPCToolkit? Well, it's easy to profile unmodified application binaries. It's fast, it has low overhead support for measurement, it's informative, it'll tell you where an application spends its time and why. The call path profiles will associate metrics with the application source code, and the hierarchical traces can help you understand the execution dynamics. It was designed for a broad audience, so we built it for both application developers as well as framework developers and runtime and tool developers like ourselves. And so, in fact, we use HPCToolkit to analyze our own the performance of the tools themselves and help us tune it and make it more scalable. And finally, unlike the vendor tools, we support profiling and tracing at exascale. And so you should be able to collect and analyze information at the full scale of exascale supercomputers. So here's the overall workflow for monitoring GPU accelerated applications. There's 4 tools. There's HPC Run, HPC Struct, HPC Prof, and HPC Viewer. And I'll tell you a little bit about what the role of each of these tools are, and then a little bit about the internals, which are interesting in their own right. So first, when you're using HPCToolkit, you compile and link your source files into an optimized binary the way that you normally do. And so one thing that's important is if you want mappings back to anything in more detail than just procedures, in fact, you have to add like a -G or -line info or something like that to the compiler arguments. And so this may require you to just tweak your make files in order to make sure that in addition to optimizing your code, you're also having the compiler record these mappings. Otherwise, we don't need it to collect performance information. But if you want to understand performance information at more than the routine level, you need to have -G in your make files. So HPC Run profiles execution on CPUs and GPUs. And so you use HPC Run to launch your application. So you might say MPI run, HPC run your application. And so HPC Run collects profiles and optionally trace files. So to measure CPU and GPU accelerated programs, it's using sampling on the CPU using Linux timers and hardware counter overflows. We get callbacks when GPU operations are launched and sometimes when they're completed. We get an event stream for GPU operations, and we can collect instruction level performance measurements using PC sampling on AMD, Intel, and NVIDIA GPUs. And we can also do binary instrumentation of kernels on Intel GPUs. So to attribute performance information, we're using call stack unwinding to attribute costs in context. And so we can set up timers or hardware counters. And so let's say I set a timer to go off 1,000 times a second. And so when the timer goes off, we'll find that we're at some particular instruction, perhaps in some routine C when called from B, when called from A, when called from main. And so that's one sample. And so that's attributing cost to this full calling context. And over time, we're going to sample a number of different calling contexts and we'll assemble them into a tree. And so the result of the collecting our measurements with this calling context profiling is we'll have a calling context tree, and then there's going to be costs attributed to each of the nodes in this tree. And the costs can be things like time or cache misses or GPU copy costs or GPU kernel execution time. And so not only are we unwinding the call stack when we get samples on the CPU, but anytime we launch a GPU kernel, we're also unwinding the calling context to find out where the kernel was launched or when a GPU copy was initiated. And so if you think this is simple, it's actually not. We can use, in some cases, we can use information from the compiler, but in other cases where compiler information is not available, where we're dealing with libraries that strip code, which is actually common for many of the libraries that are available on supercomputers, we do on-the-fly binary analysis to figure out how to unwind the call stack on x86. And so this was in a PLDI paper in 2009. So one of the things that we do is we're doing PC sampling on GPUs. And so what this is doing is we're collecting instruction level performance measurements. And so initially, NVIDIA only had support for using hardware counters to monitor the execution on GPUs. And so back in 2013, we engaged them and we urged them to add support for PC sampling for instruction level performance measurement. We had some discussions with some of their hardware engineers. And then starting in 2014, they added support for PC sampling in the Maxwell GPUs. And they've had some refinements over time that have improved control over sampling frequencies, latency samples, and support for lightweight PC sampling. And I'll talk a little bit more about the PC sampling support in just a minute. And then in 2019, as part of the Exascale project, we urged AMD and Intel to follow the lead of NVIDIA. And so Intel included support for PC sampling in their Ponte Vecchio GPUs, and AMD has hardware support for PC sampling in their MI300A GPUs. And they also provide software support for PC sampling on their MI200 series, which is used in the Frontier supercomputer at Oak Ridge National Lab. So what PC sampling on NVIDIA's GPUs does is within each streaming multiprocessor, every P cycles, and you get to pick what P is going to be. And so think powers of 2. And there's a warp scheduler on each SM that is going to decide where we're collecting samples. So there's 4 warp schedulers, and so for one of the warp schedules, we're going to collect a PC sample. And so this is done by the hardware. And then the sampling rotates round robin across each of the 4 warp schedulers. And so what happens is at any point in time, we'll look at the hardware, we'll look at the instructions that are on deck for executing. So they're like the next instruction. And so as it rotates through the warp schedulers, it will pick one of the instructions that are available. And so it'll look to see if the instruction is stalled, or if the instruction is ready to be issued, or if the instruction is ready to be issued but is not issued. It's eligible to be issued, but it's not. And so over time, what's going to happen is we're going to sample instructions across each of the warp schedulers. And what's of interest is if my instruction is stalled, but other instruction, if the sampled instruction is stalled, but other instructions are available to execute, then we don't really care why I'm stalled, because the latency is going to be hidden by multithreading. However, if my instruction is stalled and every other next instruction is stalled, then we care about why I'm stalled, because I'm an example of why the stalls are why stalls are happening. Okay, so the kinds of GPU instruction stalls are, you can be stalled waiting for memory, or stalled on the scoreboard waiting for a memory or pipeline dependency, or for instruction fetches or branches or synchronization, or you can't issue any more memory operations because the load store queue is full, or you can't issue, say, arithmetic operations because the pipelines are full. And so GPUs, as I mentioned, use a high degree of multithreading to hide stalls, and we're not really interested in the reason why an instruction stalls unless an execution unit is idle. Otherwise, those stalls are just going to be hidden by multithreading. And so we collect information about stalls when they're uncovered. So for the attribution of PC samples in NVIDIA GPUs, their CUPTI performance tools interface, we'll provide attribution for serialized kernels. We get correlation IDs that enables us to attribute these to the kernel launch context. If we're not serializing kernels and we're collecting about concurrent kernels, then in fact we get no correlation IDs. And so what this means is we know that I was in some kernel F, but we have no idea which thread called F or where. On Intel GPUs with concurrent kernel execution, there's no correlation IDs. We built support for serialized sampling in HPCToolkit that enables us to attribute to a kernel launch context. And so if you want to understand what's going on inside your kernels and you want to attribute back to where the kernel was launched, then we figured that serialization was useful. And so you just decide whether you want information inside the kernels or not. And then finally with AMD, we had a deep engagement with AMD, and in fact, they added support so that for all PC samples, even when we're concurrently executing kernels, we have correlation IDs that enable attribution back to the host kernel launch context. And so this was kind of a big deal because there was some significant software implementation inside their GPUs in order to provide this capability, and they provided this capability at our request. And so now that we convinced AMD to do it, we want to shame Intel and NVIDIA to doing it as well. So inside HPCToolkit, as I mentioned, we're collecting information inside highly multi-threaded programs. And in fact, with AMD's ROC Profiler, in fact, we're getting information coming off the GPU and it's being delivered to multiple monitoring threads. And so there's one monitoring thread that's monitoring the invocations of memory copies and kernel launches and things like that, and it's getting timing information. There's another thread that handles PC sampling. There's another thread that handles hardware counters. And so what we have to do is we have to route the information from the monitoring threads, and we have to route it back to the application threads where we want to attribute it. So we want to say that thread 1 launched a kernel at a particular point and the kernel execution took so long. Or thread 1 launched a kernel at a particular point and we had a whole bunch of PC samples inside that kernel. And so the thing that we do is we use these MPSC queues. So we built something called a multi-producer single consumer queue. And so this is a novel concurrent data structure. For those of you who understand the properties of concurrent data structures, it's a weight-free, non-linearizable concurrent data structure. And so weight-free is a big deal. This means that the application thread never waits for a GPU monitoring thread to deliver data, and the GPU monitoring thread never waits for an application thread to extract data. And so they're weight-free. We had to sacrifice linearizable in order to get a practical weight-free data structure, but the bottom line is that this enables communication between the monitoring threads, between the application threads, and between the application threads and some threads that are recording traces in the file system. And so this is important because it means that if we were using, say, a thread with like a locking queue, then we might disturb the execution of the program by locking on data structures inside HPCToolkit. So by using highly concurrent data structures, then our profiler doesn't get in the way of the execution of the GPU accelerated program. So the second tool in our toolbox is something called HPCstruct. And so it analyzes CPU and GPU binaries to recover program structure. And so what I mean by this is we've built a multi-threaded code that will analyze CPU and GPU binaries. And so we're parsing the dwarf information that was recorded by the compiler to recover information about files and functions and inline templates, inline functions, and source lines. And so that's all typical that tools do. The thing that's unique about what we do is we also analyze the machine instruction to recover information about loops and loop nesting. And so that involves parsing the machine instructions, identifying non-returning functions and branch targets, reconstructing the control flow graph, performing interval analysis on the control flow graph to identify loops and nesting, and then taking the information about the loop nests. And when we have inline code present, if we have inline function A and inline function B inside some outer enclosing function F, and we see that there's loop nests in the resulting code, we need to know whether these loop nests are in F or whether they're in inline function A, or one of them is in inline function A and the other is inline function B. And so that requires a bit of analysis as well. And so we do this with a high degree of multithreading, and we analyze multiple binaries in parallel using more multithreading so that we can analyze all of the machine code quickly, and then we cache it for the future. And there's a PLDI paper about the parallel binary analysis of these threads, of these binaries. So the next thing we do is we have a tool, HPCProf and HPCProf MPI, and what they do is they combine this program structure information, which maps machine code addresses to source code constructs, and we combine that with we use the measurement data, the profiles, and the trace files to and the program structure information to map the measurements back to the source code. So this in itself is an interesting problem, and so we built a highly multi-threaded tool for doing this that uses a technique we call streaming aggregation. And so what it does is it breaks the analysis of these performance measurement down into three phases. And so the class 1 operations correlate calling context trees and profiles. And so what this means is when we collect a calling context tree on one thread, it has different nodes in the tree correspond to different machine code addresses that we encountered when we unwound them. And every thread, every node in the calling context tree has some index in a pre-order traversal. Now, the fact that we're using sampling to collect these, we end up with different node numbers in different threads, and we have to make sure that everybody agrees. And so when main calls A calls B, everybody's going to agree that call to B is node 6 in the calling context tree. And so we have to unify the trees across threads in a node and across all of the MPI ranks in a program. And then second, we want to attribute the per profile data to this unified calling context tree. And so we'll get a per thread profile for every thread in the entire program, and then also analyze the execution traces. And so the execution traces basically say that I was in node 6 at time t, and I was in node 22 at time t plus delta. And so we need to rewrite the traces to say, well, when you measured it, you called this node 6, but after everybody agreed, what I called node 6 is now called node 72. And so we have to rewrite the traces so that to make sure that they're all coherent. And then finally, we aggregate the profile information across all of the threads and ranks in a program. And we exploit concurrency. And so this is showing the interleaved execution of these three phases, the class 1, class 2, class 3. And the only thing that is required is that class 1, 2, and 3 is in order for each individual profile. And in fact, the 1, 2s, and 3s can interleave, and they're aggregating information into a concurrent data structure. When we do this for very large-scale measurements that are collected across an exascale system, then in fact we want to use an MPI program to do this. And so we're using streaming aggregation within each MPI rank, and then we're using MPI reductions across the ranks. And so we have to unify the whole calling context tree across everybody, and then we can do the the analysis of the individual profiles and the updating of the traces and the aggregation in a second phase. And I'll show you what this looks like in just a minute. And so one of the things that became important for GPU accelerated programs is we found that the performance data is naturally sparse. And so, in fact, if you're collecting for GPU accelerated programs, there's no GPU performance metrics, no GPU instruction stalls for CPU contexts. And also for GPU code, often we have lots of metrics. So maybe tens of metrics for GPU kernel launches. Or for GPU instructions where we have instruction stalls. And so by using a sparse representation where we have each individual profile is a plane, and then each individual metric has a column, and then each individual calling context has a row. We have two representations. We have something that we call profile major sparse and context major sparse, and that just refers to which order we're which value we're indexing the planes by the profile number. Think of this as like the thread ID, and then the context, which is like the context is something like main calls A calls B is going to be some row in this. And so we found that we were able to save over a factor of 1,000 on some GPU accelerated programs. And so this is important if we're going to collect measurements at scale. And then finally, the HPCViewer user interface presents profile and trace views. And so this shows the source code interface. And so it has a source pane, a navigation pane, and a metric pane. And it's got some view control for looking at top-down, bottom-up, and flat views, and some metric displays. So the interesting thing here is when we look at a calling context, we have the function calls in full calling context, inline procedures, inline templates, outlined OpenMP loops, and loops. And so there's this interleaved, augmented context that is very rich, and this comes from combining the binary analysis results with, in fact, the calling context that we dynamically measured during the execution. So to understand the temporal behavior, in the profiles, we're collapsing out the time dimension. But to understand the behavior over time, we actually collect a series of samples for each individual thread and for each individual GPU stream. And the samples are a calling context. And so at the top of the calling context, the blue might represent main, and then maybe the green represents something that main calls like run, and then maybe the yellow represents init, and then the magenta represents solve. And then as we go lower in the profile, then there's like details of the solve, and maybe it's calling matrix vector multiplier and MPI and whatnot. And so when you look at these profiles, you can look at them at multiple levels. You can raise the level all the way up to the top and see that, like, at the top level, main is called by everyone. And then as we look down lower, then we'll find that there's differences. And so the idea is that this multi-level analysis facilitates understanding of this complex data. So here's an example of a trace view with HPCViewer. And so on the vertical axis, we have MPI ranks, OpenMP threads, GPU streams. There's time flowing from left to right. There's a detail view, and this is showing what the call stack looks like at each point in time that's shown across the display for the selected thread with the cursor. The cursor, the color here represents, so the cursor has a call stack that's associated. So what this says is that on rank 93 at 86 seconds into the execution, this is the call stack. And the color that's at a particular point on the timeline indicates the CPU procedure or GPU kernel that's active at that time at the selected call stack depth. And so on the left, you can see that there are these long purple spikes. And what this indicates is that this initialization phase is doing some computation that's represented by purple. If I want to find out what this is, I could just select where over here, and it would tell me what the calling context is for that. And then here we're like waiting in a barrier, and then there's like a sharp synchronization where everybody arrives at the barrier when the last thread finishes, completing the first phase. And so there's some load imbalance here, and so there's a lot of waiting while waiting for the slow thread to catch up. So, and finally, there's a little mini map in the bottom corner that shows the portion of the trace that is being viewed. So here's an example. So this is using our own tools to like analyze the performance of HPCToolkit's components. And so we're analyzing a 7 GB TensorFlow binary, and we do this in 77 seconds with 32 threads. And the first phase here is analyzing all of the dwarf information that's recorded by the compiler. The second phase here is analyzing all of the machine code. There's some idling between the end of the first phase and then preparing for the binary analysis in the second phase. And then we assemble all of the results that we put out for use by HPC Prof. And so if we didn't use parallelism here, this actually took about 35 minutes sequential before we investigated adding parallelism to this. And so then this is showing using the trace view to show analysis of 38 gigabytes of data collected for 2,000 MPI ranks using 1,000 threads to do the analysis, and the analysis completes in 41 seconds. And so the idea is that if we're collecting performance data for large-scale executions, then we want the analysis to be fast, and we do that by using large-scale parallelism. So some case studies to give you some insight into how this tool is used. I'll look at a couple of applications that are open source developed by the community. So the first is ExaWind, which is a wind farm simulator that's been developed as part of the ECP project. And so its goal is to simulate a wind farm with tens of megawatt scale turbines dispersed over an area of many square kilometers of complex terrain. And so the code itself is a coupled code. And so it has AMR Wind, which handles structured grid flow between the turbines using 1 core per GPU. And so this is using AMR-X, a block structured adaptive mesh refinement. And then Nalu Wind, which is handling unstructured CFD over the turbine geometry, that runs on the node's remaining 56 cores. And so the remaining 56 cores are here on Frontier, where there's 8 cores, 1 core per GPU tile, plus 56 CPU cores. And so we have this coupled code running on the system. And so this is what's simulating. So we've got the turbine blades that are spinning, and they're generating a wake behind the blades, and there's a more complicated wake that's being modeled with an unstructured mesh behind the turbine hub. And so this shows a pair of turbines. This is over time that we end up with this very complex pattern of turbulence and pressure. And the thing that they're really simulating is these full wind farms. And so it's a big problem. So when they used HPCToolkit, they collected traces on about 64,000 MPI ranks and 8K GPU tiles for about 17 minutes. And so they were able to collect this with HPCToolkit basically by launching their application with it. And the red over here shows MPI weighting, and they were using non-blocking sends and receives. And so they identified that MPI weighting was a significant problem in their application. And then after some discussion with the folks at Oak Ridge and the Center of Excellence, they replaced their non-blocking sends receives with I-all to all-V, and the time for the waiting for MPI just basically dropped out. So the important thing is that they were able to improve their performance at the large scale by a factor of 24. And that they found it easy to use HPCToolkit to do this for a very complex code. So looking at GAMES, which is an ab initio quantum chemistry package, it calculates energy, structures, and properties of a wide range of chemical systems. When we looked at GAMES in the small scale on 4 MPI ranks and 4 GPUs on the Perlmutter system at NERSC, so you see that there's some trace lines have some colors, and then there's all of this blue. Well, all the blue is basically like OpenMP threads that are waiting for work, and they're pretty much idle. And so using the user interface, you can select out and say, I just want to see the GPU ranks. And if you look at the GPU ranks and then you zoom in, then you find, in fact, that there's some load imbalance. And after some discussion with the application team, we found out that they had a problem that was basically like a triangular problem, and they were giving every rank an equal number of rows, and that led to the load imbalance. And so after we discovered this, then they changed their partitioning strategy and were able to collapse out some of that load imbalance. And so this was within a cooperating group that was simulating the movement of a set of monomers and dimers. And so then when we looked at, after they improved the program, we looked at it on a larger scale on 5 nodes with 40 ranks and 20 GPUs. And so collapsing out so getting rid of the CPU threads and just looking at the GPU streams, then we could see here that there's like a major load imbalance. And so obviously a bunch of this work that this this group of 4 GPUs has much more work than the group at the bottom. And so the load imbalance was a serious problem. And so then we sent the application team back to look at how to use bin packing to do a better job. And so they worked on improving their load imbalance. Another thing that's interesting is you notice that on the right there's these green kernels, and everything between all of the white spaces is idle time. And so the interest was, well, why are these kernels separated? If we want higher GPU performance, we can either tune the GPU kernels or we can make sure that the GPU is more active. So we can use HPCToolkit to just reveal what's going on the CPU and then zoom in and look at what's going on and find that there's this OpenBLAS DAXB call. And so then go looking in the source code, and we find that they implemented a symmetric matrix multiply. So this was an implementation that was done back in the 70s or the 80s. And what they really should have done is called an OpenMP routine for symmetric matrix multiply instead. And so if they used a parallel routine to do this, then they could use some of those idle CPU threads to shorten the time for the operation, and then get the GPUs more active by reducing the serialization waiting for the CPU. This is something that was done in a hackathon a week or two ago. And so they were looking at Pele LMEX. And so the goal was to simulate operation of a synthetic aviation fuel-based gas turbine. And so what they found was that, in fact, there was a significant load imbalance across the GPUs. And so after some consultation with the Amrex team, they were able to turn on identify that there were that they could turn on regridding. And after regridding, in fact, the load is much more balanced across the GPUs. And so the trace view in HPCToolkit is useful for understanding when you have these kinds of load imbalances, and then what you do with it kind of depends upon the software that you're working with. Another interesting case was using PC sampling with Pele-C and on NVIDIA GPUs. And so what we found was that 9.4% of the GPU stalls were attributed to this particular loop that was executing in the GPU code. And however, the stalls were outside the loop. And with a bit of thought, what we came up with was, in fact, the way that they were passing the data into the GPU with their closures, they were passing a structure. And so basically, to access elements, we're taking page faults over unified memory. And so by changing it so that they weren't passing a structure, so that they were passing scalars, then they get passed in constant memory. And so by changing the way the lambda function was handled here, they were able to get a 4% speed up over the entire application. And so this is just an adjustment to the GPU kernel, and this only came from using the detailed binary analysis within the GPU kernels. And then finally, Quicksilver, just to show you something interesting, what we're doing with the PC sampling. So Quicksilver is a proxy application for Lawrence Livermore National Labs Mercury code. And so Mercury is a dynamic Monte Carlo particle transport solver. And they have about 100,000 lines of code for the application, and it's all inside a kernel. They decided the easiest way to parallelize this on a GPU was basically to take the entire application and shove it into a kernel. And so there's thousands of procedures and 100,000 lines of code. And all of that happens inside a kernel. And so if you just told them their kernel's slow, that's not good enough. They need to know why the kernel is slow and what the kernel's doing. So, we collected PC sampling information within a kernel for Quicksilver, their proxy application. And what this shows you is inside the GPU kernel, there's a GPU kernel cycle tracking kernel, which on line 132 calls cycle tracking guts, which calls an inline procedure, which has a loop inside it. And so there's inline code. And so basically what you can see is that using our binary analysis and using the PC samples that we collect, we're able to recover the program structure and attribute the cost to the program structure in detail. So how do we do that? We're collecting flat PC samples, and we're reconstructing an approximate calling context tree to attribute the costs within the kernel. And so the first thing we do is we construct a static call graph based on the functions and the call instructions. And so and then we initialize counts for all of the edges based on either in this case with the samples of the call instructions that we took in the code. And if for measurements using samples, we might find that we take some sample in some procedure B that where we never actually sampled the call instruction because we're sampling. And so in that case, we can tell we were in B, so we must have crossed this edge from A into B because that's the only way that you can reach B. So we do a little bit of data flow analysis and we propagate some costs around. And then we identify strongly connected components where there's functions that are calling back and forth between one another. And then we build a calling context tree by splitting the call graph. And so here we have C and B are both calling this strongly connected component that contains D and E. And so we split this into pieces. And then the costs that were measured in here, we're going to split the costs according to the edges. And so this says that there's 2 calls here and 6 calls here. And so this gives us 2/8 and 6/8 are the costs that we attribute to each of these contexts. And so this is approximate, and it's based on the gprof assumption that basically all calls to a function cost the same. And we know that that's not true. That some calls to matrix multiply, sometimes you're calling matrix multiply with a large matrix, sometimes with a small matrix. But it's the best approximation that we can come up with without any other information, and it usually gives you useful results for code. So finally, with LAMMPS, LAMMPS is a molecular modeling program, and we collected some large-scale performance data on Frontier with 64K MPI ranks and 64K GPU tiles. And so when we were using kernels that were launched for milliseconds, it's an SPMD code. And so what we were expecting is that they're kind of like tightly synchronized columns where what we're showing here is just the GPU execution. And so basically we expect everybody to be executing on the GPU at the same time. And so we would expect this like tightly synchronized SPMD behavior. When we looked at this, we can see that there are these weird effects here where there's some delays, okay? And so clearly there's some disruption like basically at the start of every major iteration that is affecting the performance. And so when we went looking inside, and so the previous figure was just showing the trace lines for the GPUs. Here we're revealing a few trace lines for the CPUs. And then we went and clicked in here to say, well, what's actually going on in the CPUs while the GPUs are idle? And we found that we're in MPI send and receive. And so then the question was, are the sends and receives, are those the cause of the delays or are those an effect? And so after some discussion with AMD, the idea is that maybe actually they're an effect. The AMD thought that there could be delays associated with GPU scratch space reclamation. And so we asked, well, can we measure that? And the answer was no. So since we're getting this information from AMD's measurement interface, we said, well, if there are things that can take arbitrary amounts of time, we need to be able to measure that. And so we don't have the ability to measure it ourselves because they're providing the information. And so we got them to add support for measuring this scratch space reclamation and some other important things into their measurement interface so that we could try and explain what these delays were. And then also in HPCViewer, you can look at a calling context where here it says the context for MPI send, and then plot the MPI send cost across the execution context. So some of the execution contexts are GPUs, which are not doing the sends, and then the CPUs are doing the sends. And you see that there's this this big distribution. So some of the processors are sending for less than 50 seconds, and some of them are sending for more than 150 seconds. And so, this is something that's really of interest in trying to understand the large scale behavior. Unfortunately, by the time that the machine was stable and the tools were in good enough shape to collect measurements at scale, we only had time for one run before we no longer had the ability to collect, to use the machine at scale with unlimited execution time. And so we haven't been able to sort of fully diagnose this problem. We got a chance to measure, but that was it. And so this also shows that we can do like a histogram view of the communication as well. Here's something else where we measured lamps on 8K nodes with 64K MPI ranks and 64K GPU tiles. And the kernel duration was microseconds, and you can see all of these strange patterns of propagating delays. And so what we believe is happening is if someone is delayed, and in lamps you're doing this modeling where you're doing like molecular dynamics for a volume in space, and you're communicating with your left and right, up, down, front, back neighbors. And if you get delayed, then your right neighbor is going to be delayed waiting for you, and their right neighbor is going to be delayed, and that results in sort of a propagation of delays. And so then the waves collide and cancel and whatnot. And so the question then was, what's the root cause of these delays? Is this like still like the GPU scratch space reclamation, or are we just pounding on the slingshot interconnect so hard that that it's causing congestion? And so we started using hardware performance counters to look at slingshot, but we didn't get a chance to do that on Frontier. We moved to do that on Aurora. Then Aurora went down for acceptance testing, and so we haven't had a chance to dig into that in detail either. So our support for GPU accelerated systems is summarized as follows: is that we can do coarse grain profiling, instruction level measurement, tracing, and binary analysis. The support for the Intel GPUs is sort of still in its infancy, and the reason for that is that there's some limitations in Intel's measurement infrastructure. So in particular, when measuring using Intel's level 0, when we want to do PC sampling, we have to record the GPU binaries in order to interpret the samples that are associated with machine instructions. And it turns out that the GPU binaries vary across the ranks. And so basically the binaries that we get back are influenced by the state of the memory allocator inside each MPI rank, which is just madness. And so we told them, look, neither NVIDIA nor AMD do this. You need to do better. And so we're still waiting for them to resolve that. Also, the way that we're measuring with level 0 is we're intercepting calls to level 0. And level 0 is very complicated. There's queues, and there's command lists, and there's immediate execution of command lists and delayed execution of command lists, and on a big interface to monitor. And it's very hard to monitor. And so they started building something that they're calling PTI GPU, which is kind of like NVIDIA's CUPTI interface, but it's still in its infancy. It only has about 50% of what we need. And so we're kind of waiting for this to resolve so that we can actually do what we would like with our tools. And then finally, we're using Intel's GTPin to collect instruction level measurements as well. Not only their PC sampling, but we can do instrumentation and do like basic block profiling and look at the utilization of scalar instructions and vector instructions. But it fails for some complex GPU binaries, and so we're waiting for some of those issues to be resolved as well. And then for the AMD GPUs, the software support, they have hardware support for PC sampling in the MI300A. While we have access to MI300A systems, we don't have software support that provides access to the PC sampling hardware. And so we're waiting for that from AMD. And then just a few notes about CPU measurement infrastructure. It turns out that glibc lacks a foundation for safe thread local storage. And this is a real pain if you're trying to build tools that are multi-threaded. So thread local storage itself is not async signal safe. So if you declare thread local variables in C++, you can't use those inside signal handlers. And you might think, oh, well, I'll just use pthread keys. It turns out that if you're using multiple namespaces, and the reason why multiple namespaces are used is that tools often use their own copy of libstandard C++ that you can't guarantee that an application is going to use the same one. And so you put these things in separate namespaces. If you have multiple namespaces, pthread keys get assigned individually inside the individual namespaces. And so one namespace can say pthread key 6 is used for something, and the other namespace says pthread key 6 is used for something else. And then when they actually try to access the thread local storage, they collide. And so it's chaos. There's a Bugzilla report, was filed in 2019, and it's still an open bug. And then we've been working with the glibc community on something called LD audit, and so this is better than wrapping functions to monitor things. And so you can put a wrapper, like we can declare a version of pthread create inside our tool. So whenever pthread create gets called, we get to intercept the call so that we know that a thread has been created. It turns out that you can't use this wrapping if you're like extensively using dynamic libraries and DLSim and calling things through function pointers. And so LD audit is a better interface. In 2021, we wrote a manifesto that described about 14 bugs that you just couldn't get around, where it would cause things like uncatchable failure or factors of 10 slowdown. And we got those fixed by the glibc community, but there's still some issues that need to be resolved. So finally, just a bit about the ongoing work in our group. And so we're working on releasing the new measurement capabilities for PC sampling on AMD and Intel GPUs. Those are working in branches. The NVIDIA stuff has been in our mainline release for a long time. And we're still working things out with the vendors so that we can release this code. One thing that's important to note is the strategy that I was describing for attributing PC samples inside complex kernels. While it works for typical codes, it does not work for the code that we really wanted it to work for, this Mercury code that has 100,000 lines of code inside a kernel. And what we found is that some of the program counter locations had 500,000 paths by which you could reach an individual instruction. And so we decided that we had to move from using calling context trees to using a DAG-based approach for attributing kernel level performance. So this will give us the same attribution that we would get using the trees, except it's a much more scalable approach. And so this is work that's underway. And so this is for doing fine-grained instruction level monitoring of things at scale. And then we're also looking at analyzing the behavior inside complex kernels. And so some next steps are actually interpreting the performance measurements, some automated analysis, and some features to support AI workloads. And so just to provide a little taste of something that's going on right now, one of my students is working on understanding activity within an individual GPU kernel. Now, some kernels, for vector add, like everybody who is computing on a position less than the end of the vector just performs the same code. For this quantum Monte Carlo code, for this dynamic Monte Carlo code, Mercury and Quicksilver, its proxy application, they're running a Monte Carlo solver inside the kernel. And so what this is showing is the individual threads within an individual kernel. We're showing traces of the calling context that they're executing. And so this is what the calling context tree looks like over time for an individual thread during its execution. And then it's just showing sort of the pattern of concurrency. And what you find is that while you start out with a reasonable amount of concurrency, the concurrency sort of dwindles over time. So that basically you're not getting full value of the data parallelism over time in some of these complex kernels. Okay, so that's basically what I wanted to tell you today, and I'd be happy to answer any questions about this work, and I'd also like to discuss some of the things that you're doing as well. Yes.
Thank you, John, for the great presentation and for working on tools that are so useful for the community. So in case anyone wants to ask a question, raise your hand and I will unmute you or put it in the chat, and I will read it out for others. So let's start with Alexandru.
Hello, thanks for the really cool presentation. So I think that the most valuable thing is the actual impact you had on applications. So the case studies that you've shown are really cool. I have two questions. So one is, especially for this kind of fine-grained measurements that are very useful in getting this insight. So often overhead of the measurement itself is problematic because it can sometimes skew the results. How do you handle this? Is this not really relevant for your kinds of measurements, or do you have to fight it?
So I'll tell you two things. So when measuring on the CPUs, you can basically dial down your sampling frequency, and so that the overhead can be roughly as small as you want. Okay. When collecting the instruction level performance measurements on the Intel, sorry, on the NVIDIA GPUs, there's actually hardware support for collecting the instruction level performance measurements, and we can also select the sampling frequency on that, and so they can sample as often as maybe every 1K instructions, or you can sample at a longer period. And so as long as you sample it like at a reasonably distant period, not every 1K instructions, but maybe every 30K instructions or something like that, that the hardware basically can do this measurement without actually slowing down the kernel. Now, there is time for like transferring the measurements from the GPU back to the CPU, and then for the CPU, for the tool to record it. And so our rule is like, if you're collecting measurements within a GPU kernel, then you shouldn't really pay attention to like the timing of the whole thing, because it's going to dilate the execution. So you like measure it once without collecting the information inside the kernels, collecting your tracing information to see what the execution dynamics look like. And then second time you collect the detailed information inside the kernels, and then you can get accurate information inside the kernels without sort of caring about like how the overhead of that affects the overall collection process. Okay, so I think that you can get good information inside the kernels without it being affected, just because we're using the hardware support to do this. Now, on Intel and AMD GPUs, I don't think that they have the same level of hardware support for this. And so, in fact, they're using like a timer to collect the information. And I don't know that they have hardware support for aggregating it. And we don't have enough experience with their GPUs to look at, to basically like look at overheads. And so with Intel, the big concern is that we have to serialize kernels in order to collect, to collect and attribute the information at all. And so there's an overhead associated with serializing the kernels. Does this have an impact on the execution time of the kernels while we're measuring them? That isn't something that we've looked at yet. Okay.
Okay, cool. Thank you very much. That was very enlightening. Thank you.
Okay, Sean.
Hello. So really nice presentation as well. So the question that I have is sort of similar to the one that's asked by Alexandru. So essentially regarding the overhead of the tool chain itself. So on slide 22, I think you mentioned that I think periodically or something you aggregate data from these MPI processes with reduction or something like that. So I'm just wondering how much data you're actually aggregating and what kind of performance impact this might have on the network itself. Since, if you're running like 64K processes and you do this kind of a reduction, you might have like a really huge incast on the network, and that might really affect the performance of the application that's, running in the cluster. So I'm just wondering if you measure this kind of an overhead.
We don't measure it, but I can tell you that the overhead is zero. And the reason is that when we aggregate the performance measurements, we do that all in post-mortem analysis. We don't do the aggregation as the program executes. Basically, we collect the data for each individual thread, each MPI rank, and each GPU stream separately. Okay.
Okay.
And then we aggregate all of this during post-mortem analysis.
Okay, that makes a lot of sense. And also regarding the size of the traces as well. So how large, so maybe I missed this in your presentation somewhere, but I'm just wondering how large the traces actually are.
Yes, so that's an excellent question, because the traces for NVIDIA's tools grow exceptionally quickly. So our traces are relatively, I'm going to say relatively small, and then I'm going to say the word terabyte. But which
Okay.
okay, so when I say that they're relatively small, so for each individual event we're tracing, it's only 12 bytes. And so what we have is essentially a node number in a calling context tree that says, I was in routine MPI wait when called from the ocean phase of the climate application. Okay, so we have the node in the calling context tree represents the full calling context, and then we have a timestamp, and that's it. And so we have 12 bytes per entry in the trace file. Now, for CPU traces, the CPU traces are relatively small because in general, we're sampling the CPU about 300 times a second. Unfortunately, we don't get to control how often you invoke GPU kernels. And we do record an entry every time a GPU kernel starts and finishes. And so for like a GPU kernel execution, that's 24 bytes. And for a GPU memory allocation or something, or deallocation, that would be 12 bytes. Because all we have to do is, actually, I'm sorry, those are also 24 bytes, the start and end of each of those operations. So for something running, for this LAMMPS code running on 64K GPUs, running kernels that were executing for microseconds, it ran for 17 minutes, and we collected 4 terabytes of data. Okay. It turns out that that's a relatively low I/O rate, and so we're only writing out a buffer for a thread every time we collect a 2 megabytes of trace. Then we'll asynchronously send the buffer to the file system. And if you've got a flash-based file system, then the writing is quick, but in any case, it's overlapped with the program execution. So the traces can get to be large. You can collect traces for just like some portion of the program. You use like on-off calipers. You might say, I want to measure a couple of iterations up the front. I want to measure a couple of iterations after a while, after some adaptation has taken place with AMR. So you don't have to collect traces all the time. And in fact, you don't have to collect traces at all. So basically, people will use the traces to try and understand these complex execution dynamics at scale, but they don't have to do it for, an application that's going to run for a week. Okay.
Yep. Thank you for your explanation.
Thank you. Nikos?
Hello, thank you very much. I'm a bit overwhelmed by the complexity and the in-depth presentation of your work. And I have a rather simple question. What is good practice? Do you keep the traces? Like, for example, all these applications that you helped to improve. Do you then keep the logs and the traces as a proof, as an evidence for further analysis, or do you erase them? Because you mentioned that relatively small, but we're talking about terabytes.
So when I mentioned traces in terabytes, that was we only had terabytes for this one trace that was executing GPU kernels of microseconds. So often, if you're running sort of smaller scale traces and you're trying to tune a code and you're working on 30 or 100 ranks or something like that, and running something for some number of minutes, maybe 10 minutes or something like that, then the traces are sort of modest in scale. They might be under a gigabyte or a few hundred megabytes or something like that. And so for those things, we keep them. For the couple of executions at very large scale, we did keep them. Okay, we did keep this 4 terabyte trace because we only had one chance to collect it. And so we're not going to throw that one away. But in general, I think for these very large scale things, you can't really afford to keep them all. You like to sort of analyze them, get the information you're looking for out of them, and then throw them away. And so I have one student who's actually working on automated analysis. And we found that, in fact, even for those examples with lamps where you're seeing like all of that wavy behavior, you actually don't have to look at every rank in the trace, because everybody has sort of similar behavior. And so what we want to be able to do is like use sampling to sample individual profiles and sample individual traces, and then look at enough and be able to quantify whether we have looked at enough to understand the performance, and then provide some feedback to you about what the problems are with your program without saying we have to look at it all. You don't really want to say, here's this viewer where you're interactively going to look through these very long traces on large scale stuff. So one thing I didn't mention is that when looking at, we can use our interactive viewer to look at these 4 terabyte traces. Right now, like we were looking at this interactively over the internet with the 4 terabyte at Oak Ridge, and using our X11 based interface on a virtual desktop at Rice, it would take about 10 seconds to render one of these views looking at the 4 terabytes. And that's like too slow for ideal. And so we're working on a better remote interface, but that's not bad for like a virtual desktop running over the internet. So I hope that answers, various aspects of your question.
Yes, I think so. My understanding is that it's a case by case. Some you keep and maybe. Thank you.
Okay. Anyone else? If not, I have a question myself, actually. So from what you've shown us is that getting this actionable information, right, from the traces takes a lot of manual effort, right? So as an engineer, I need to go through the trace, I need to look through it, I need to do a lot of work to understand why and how and what do I need to change. And you also mentioned that this work that you're doing for the future, that you're working and looking at automated support for that. So I was just wondering, like, what direction are you going there? Is it sort of like pattern matching, or like how do you approach that?
So I'll say 2 things. One is we built this tool called the GPU Performance Advisor. And so this is like this is work that was principally done by my graduate student, Karen Zhou, who is now a faculty member at George Mason University. And what Karen was doing was we were looking at like the individual GPU, like the instruction stream in the individual GPUs. And so like basically by analyzing the machine code, we would find that like delays occurred at some place, and like we were waiting for a value to be loaded, and then we would like look back through the control flow to figure out like where the loads were executed. And then we would say, well, so you have some loads that are too close to their uses, or maybe there's some things that could be improved by common sub-expression elimination, where if the compiler was better, it would have done it automatically, but it didn't. And so there's like some pattern matching there. And so there's a paper about GPA where it's using pattern matching for analysis of GPU kernels. For this large scale analysis, there was a paper by my student, Lai Wei, and what we were doing was we were looking at these large scale traces, and he basically had like a taxonomy of problems like serialization and load imbalance and things like that. And then you would basically like look at you would break the trace into intervals where there was either like nothing interesting going on because everybody's kind of computing embarrassingly parallel, or there's kind of some serialization. And then within a phase, he would identify sort of what a problem was and then quantify like what the impact would be. So if you could balance the load in this phase, then that by reducing everybody's cost to the mean cost, then how much savings would there be? And so what I would say is we're going to look at trying to scale that work, to look at these larger scale things using sampling.
Yeah, that sounds very nice. Thank you. And the second question is about different applications. So what you've shown us is those traditional applications, right, in HPC. I assume also because they have a bit more interesting communication patterns than some large-scale AI that I wanted to ask about. So have you maybe like looked at LLMs or those kind of type of workloads, or not so much?
So the answer is no. We haven't actually looked at any LLM workloads yet. I think that HPCToolkit, for the most part, we've focused on collecting information about the computation, like what's happening on the CPU. And so for message passing, what we would find is that you're spending your time in your MPI library. Okay. And so that's the way you see the message passing, is you find yourself spending your time in the MPI library. But we aren't really measuring like message volumes and point to point, and we're not measuring IO, and we're not measuring we're measuring when you're in memory copy routines, but we're actually not measuring the data movement. And I think that for AI applications, we need to understand, whether data movement from, the training examples into the compute nodes is an issue. We need to understand the data movement. We need to understand the communication more. And so I think that that instead of just looking at where we are, we're going to need to capture sort of more semantic information for diagnosis. So I think the LLMs are like, certainly they're of growing interest. And what I would say is, at the moment, with the small team that I have, we've had our hands full kind of browbeating the vendors to get the measurement infrastructure and get the hardware support in place. And we're just getting to the point where, as I mentioned, that that AMD is now about to have a finalized release of their ROC profiler infrastructure, probably in ROCm 6.5, which is 6.4 is not out yet. And Intel still doesn't have one yet. So we spent so much time on just like focused on getting the measurement right and getting the vendors to implement measurement interfaces that would enable us to do what we wanted to do, working with the glibc community to remove the impediments for measurement, that we haven't actually had the time to delve into the AI models. And that's something that obviously is of interest. And so right now I'm on sabbatical, and my focus is like looking at things at the intersection between HPC and AI. And so the goal is to try and finish up some of the core support and then start looking at some of the AI workloads and what we really need for that.
Yeah, that sounds good. And thank you for doing the work for the community, right? So the tool is amazing, and with people like you, we can push the vendors to actually get stuff that we need, right? It's a very important part of them.
And I would say that this has sort of been an interesting transition for my group, because it started out as a research project, and then it turned into something where it was like a combination research project as well as releasing tools for the community. And I was only able to do that because I was able to get enough support from the US Department of Energy to actually fund some staff, so I could get the students working on the interesting research problems, or students and postdocs working on interesting research problems, and then the staff like transitioning these things from research prototypes into like hardened capabilities that would run on like arbitrarily complex programs at the national laboratories. And so I'm not sure where Torsten's group falls in this case. I know that there's a lot of things going on in the group. So I had a question. Is anyone here involved in the Scalano work?
So I'm not. I don't know about anyone else in the call.
I know that Torsten was involved in this, and I'm not sure whether there were additional people in the group that were involved in this. So this was basically like collecting graphs and then interpreting these, like analyzing the graphs to try and identify performance bottlenecks post-mortem. And so I'll just send Torsten some follow-up email, because we've been talking about that as we're looking at sort of scaling up our automated analysis capabilities. So.